Hypothalamus artificial intelligence, HI. Digital transformation powered by real-time autonomous and intelligent algorithms. Presents the short conference, How do artificial brains learn math? Using algorithmic learning. In Industry 6.0. A swarm of artificial intelligence algorithms, that is the orchestration of swarms of cognitive robots on a global scale. Following the teachings of Donald Hebb, the magic rule for an artificial brain to learn is a swarm of algorithms that operate together, connect. Human brain. AI creates the most detailed 3D map of the human brain ever made. HI considers that the creator of the human brain conceived it as the integration of three main organs, or systems: neocortex, hypothalamus, and hippocampus. These three fundamental components are made up of neurons. The human brain can be conceived as composed of the following main components, or subsystems: neocortex, hypothalamus, and hippocampus. The artificial brains corresponds to the scientific foundations, more specifically mathematical fundamentals, that allow to connect multiple mathematical models, algorithms or robots, exchanging information between them to obtain a common goal, and act as holistic intelligence of the organizations, or parts therein. Like the human brain, the artificial brain is composed of the following artificial components: neocortex, hypothalamus, and hippocampus. Emphasizing that HI is not an expert in neuroscience, its interpretation of the functioning of the brain is presented. The cerebral cortex stores all the connectivity of the neural networks that make up the brain. The hypothalamus is the organ that ensures the proper functioning of the human being. The connectivity of neurons in the cortex determines how the hypothalamus should function. The hippocampus is responsible for managing memory, which interacts with the hypothalamus, to determine the actions that the human being will perform, that is, decisions. Artificial entrepreneurial brains are based on these hypotheses. HI has dedicated his research efforts to explaining his experience in the development of multi-problem mathematical models, as a fundamental step in the creation of artificial brains for the entire company. The result is the evolution of artificial intelligence based on neural networks, to artificial intelligence based on the structure and functions of the human brain. On the other hand, HI is oriented to the construction of artificial intelligence algorithms based on explicit mathematical models, both in predictive and prescriptive analytics. This eliminates, as far as possible, the subjective components of the algorithms. From the point of view of HI, one part of the artificial hippocampus processes the information stored in the other part, to develop a learning process. Learning takes the form of the generation of new neural connections, which must be stored in the artificial cerebral cortex, to be used in the future by the artificial hypothalamus. This high vision of artificial intelligence, built from the workings of the human brain, is currently unique in the world. Human intelligence. From Einstein brain to artificial general brains. Human intelligence has evolved along with human beings. To understand this process, HI describes human intelligence as composed of three intelligences. Mental intelligence underpins the mental models that every human being requires to start making their decisions. Human knowledge is supported by three types of intelligences. Mental intelligence, it is the abstraction or conception of what is perceived by individuals about a given issue or problem. Mental models are constructed with the knowledge, experiences, assumptions, perceptions, intuitions, informal inductions, deductions, and values of the individual. They are elementary models that are not exposed in public and therefore have a validity limited to the individual. They have their origin in the evolution of the human being, hominization, from the most primitive ancestors, Australopithecus, to the appearance of our species as we know it today, Homo sapiens. All human beings manage mental models, very quick to solve, and, in their absence, easily copy themselves from a more influential individual, and more recently, are implanted in human beings through the ochlocracy of mental models distributed by social networks. When intelligence works under this model, we will call it mental intelligence, which exists and develops in all humans. Mental intelligence and pattern recognition. Mental model is oriented to identify patterns, its foundations are not mathematical, and respond to data processing and evaluation of eventual and systematic experiences. It is based on good practices. Pattern recognition is a data analysis method that uses machine artificial intelligence algorithms to automatically recognize patterns and regularities in data. This data can be anything from text and images to sounds, or other definable qualities. Pattern recognition systems can recognize familiar patterns quickly and accurately. Pattern recognition is the activity that most performs the human being, for example, identifies images of people, foods, hydroclimatic conditions, traffic conditions, texts, sounds, and etc. All this with the aim of establishing the conditions of the environment, in the past, the present, and the future, and based on this knowledge make decisions. How the brain identifies patterns is not properly known, but it is mimicked by traditional artificial intelligence. Then, the starting point of the name of artificial intelligence is associated to the pattern recognition. Today, the association is direct, and it seems that artificial intelligence is reduced to this function of the human brain, what has concentrated great amount of scientific research in working in this direction, forgetting other human brain functions. It seems that artificial intelligence is reduced to the emulation of mental intelligence, whose function is little known and explained. That is why it is known by scientists that neural networks can predict how a system will behave, but that in general the parameters found cannot be explained, they have no clear content, just as the humans cannot explain how this function works in the human brain. But this approach cannot be said to have been unsuccessful, as it effectively and massively replaces activities that ordinary humans did not think machines could perform. At first, neural networks were aimed at finding ways of connectivity of artificial neurons, seeking to improve the results of prediction. Something like a statistical model in which many algebraic models are tested, until a good solution is found. Little has evolved to try to explain content in this connectivity. This is the case with GPT. Creative intelligence is the fundamental basis for the development of mathematical theories that support mathematical models. For Hebb, this is an area of knowledge that is still unknown. To evolve from mental intelligence to mathematical intelligence, the human being requires another type of intelligence that allows him to perform the analyses to understand and discover the models that govern the universe that is written in the language of mathematics, Galileo Galilei. We will call this intelligence analytical creative intelligence. This intelligence can be considered as the highest level of human intelligence, since it is what allows to grow in the discovery of mathematical laws, and in general new knowledge, which is the engine of the scientific and technologic of humanity. In practice, very few humans have this ability and discipline. Scientific thought. A scientist thinks critically, questioning the established and using the scientific method to systematically investigate the world, seeking explanations based on observation, experimentation, evidence, and logical reasoning. This way of thinking is characterized by curiosity, skepticism toward unfounded conclusions, openness to new evidence, and collaboration with others to generate verifiable knowledge not accepted by mere authority or common thinking. A scientist is characterized by the ability to ask questions about the why of phenomena and seek answers, which drives research, based on the systematic collection of data through observation and conducting experiments to test their interpretations of reality. Scientific conclusions must be supported by verifiable evidence and objective data that others can verify. He uses logic to associate concepts, generate new ideas and order knowledge into coherent theories. The scientific method is a systematic and objective process for acquiring new knowledge, which consists of observing a phenomenon, formulating a hypothesis, designing and conducting experiments to test it, analyzing the data, and finally reaching a conclusion. The main characteristics of this method are the falsifiability and reproducibility of the results, which allows other scientists to verify the findings and expand knowledge. The phases of the scientific method include observation, research, experimentation, and data analysis. The most important action is the formulation of hypotheses by finding a tentative assumption or explanation for the observed phenomenon. The conclusion of each step will be to determine whether the hypothesis is valid or not, based on the analysis of the data. If the hypothesis fails the test, the hypothesis must be changed, which involves change the basic theory. This means changing the mathematical model that explains the process, or change or increase experiments. Proof of the above is the speed with which we produce knowledge. It took many centuries, hundreds, to produce algebra, but mathematical knowledge every day occurs faster, and extends its borders. For example, since 1947, with the appearance of the digital computer, a new science has been created: mathematics for computers. First monoprocessors, today parallels. This must be part of the artificial intelligence of the future. When the previous trend changes, humanity will have begun its disappearance process. Mathematical intelligence underpins the mathematical models that some humans develop to make their decisions. While humans in prehistoric times did not have access to mathematical intelligence, because they were creating it, today it is the engine of human knowledge, and ideally should be handled by all humans. Unfortunately, this is not the case. Therefore, its management must be part of the artificial intelligence that humanity is creating. The same thing happens with creative intelligence. The knowledge created by scientists, and the way to produce it is part of today's human intelligence. Second, mathematical model is a scientific representation which make use of mathematical language to describe or to explain the portion of reality that is of particular interest to an individual. It is the result of the research carried out by certain humans. The mathematical models are growing as analytical tools that provide greater processing speed to the investigation. For its understanding requires formal training in mathematics and in the science being modeled. These models increase the intelligence of human beings, creating large differences, chasms, between them. When intelligence works under this model, we will call it mathematical intelligence. This ability to understand mathematics, and to handle it, does not extend to all humans. It is necessary to acquire knowledge and experience, to handle this intelligence properly. At present, its development is directly related to the ability to handle computational and mathematical technologies. Mathematical intelligence and decision-making. Decision-making process is the final objective of any person or organization, which seeks to make the best decisions from its point of view, its criterion. This process, when carried out in real time, requires a great capacity for mathematical calculation, to handle the complexity of the real world, which increases over time, since the universe increases its entropy at each moment. When humanity began its evolution, it only had mental models to support its decisions, which seriously limited the speed of the evolution of the species, due to the little, almost zero, capacity of mental models, which led the human being to make decisions with very few calculations, or without them. Thanks to analytical intelligence, human beings developed their mathematical intelligence, which has led us to Industry 4.0. Since the creation of AI, and the advent of the computer, it can be said that predictive methodologies displaced prescriptive ones, in what was called artificial intelligence. For the convenience of the reader, decision-making artificial intelligence, DMAI, will be presented in comparison to traditional artificial intelligence. The first big difference is that DMAI is based on the study of mathematical intelligence, which focuses on the representation of the physical world through algebraic formulas, or through differential calculus, and solves problems using exact mathematical algorithms, aimed at finding the best decisions. This area of science corresponds to prescriptive analytics. To develop creative intelligence, it is necessary to understand the lives of creative scientists and their way of working, then it will be possible to try to model that process. Prior to the birth of computers, the scientist's routine could be summarized in iterative processing based on formulation of a creative idea attached to a theory, conducting experiments with the aim of validating the theory or finding errors to reject or to adjust the theory. If the experiments validate the theory, the creative process is over. Otherwise, the theory is adjusted, and new experiments are carried out. This process can be slow, due to the time consumed in each experiment, which can include setting up the experiment environment, which could involve complex processes, mainly when a laboratory with ideal conditions must be built. The creation of computers, which are the essence of mathematical intelligence, begins to transform this process, due to the possibility of computers in the process of experimentation. As the power of computers has grown, from the ENIAC computer to today's quantum computers, the involvement of mathematical modeling is playing an increasingly important role in the experimentation process, which can be carried out automatically following predictive and prescriptive artificial intelligence principles. An automatic experimentation process, carried out by a computer, once an experiment has been performed and evaluated, could follow the next algorithm. If the experiment validates the theory, the experimentation process is over. Otherwise, adjustments must be made to the theory or to experiments. For example, adjustments to the theory may involve variations to the equations. Adjustments to experiments may involve changes to the experiment environment. It is evident that with today's computational power, this process can be very fast, and the scientist can advance very quickly in his research. The experimentation process can be enriched with predictive artificial intelligence, which can learn from real-time experiments and the history of previous experiments. Prescriptive artificial intelligence can help improve theory by formulating and solving problems that require adjustments to the equations of the theory. In this way, the scientist's learning is accelerated. Another contribution of computer technologies to creative intelligence is digital twins. This aspect is linked to the need to carry out experiments that in many cases require the construction of a physical prototype. Before the existence and growth of computers, laboratories were physical and, in many cases, were built for an experiment. Today, digital twins can function as virtual laboratories and can be linked as input and/or output of mathematical artificial intelligence, eliminating the need for physical labs. Mental intelligence, creative intelligence, and mathematical intelligence. So far, HI has developed artificial intelligence for decision-making, which corresponds to mathematical intelligence, and has ignored the development of creative intelligence, but has begun a new phase focused on creative intelligence. Everything seems to indicate that creative artificial intelligence is ready to be implemented today. When studying the scientific method, the simulation of creative intelligence must be done using a specialized model of mathematical intelligence, as it is a mathematically modelable process. HI has dedicated his research efforts to explaining his experience in the development of multi-problem mathematical models, as a fundamental step in the creation of artificial brains for the entire company. The result is the evolution of artificial intelligence based on neural networks, to artificial intelligence based on the structure and functions of the human brain. On the other hand, HI is oriented to the construction of artificial intelligence algorithms based on explicit mathematical models, both in predictive and prescriptive analytics. This eliminates, as far as possible, the subjective components of the algorithms. If you want a cognitive robot to mimic a scientist's creative intelligence, which is equivalent to artificial general intelligence, AGI, you need to teach it the principles of scientific thinking and the process of the scientific method. Predictive intelligence like GPT does not have the ability to implement AGI. Those who have chosen this option are going down the wrong path. Artificial cortex. One of the most famous neuroscientists, Santiago Ramón y Cajal, was a Spanish physician and scientist, specializing in histology and pathological anatomy. He shared the Nobel Prize in Medicine in 1906 with Camillo Golgi, in recognition of his work on the structure of the nervous system. Through his investigations into the mechanisms governing the morphology and connective processes of nerve cells, he developed a revolutionary new theory that came to be called the neuron doctrine, since brain tissue is composed of individual cells. Humanist, as well as scientist, he is considered the head of the so-called generation of sages. He is frequently cited as the father of neuroscience. And Jeff Hawkins is an advanced researcher in the application of neuroscience to the development of artificial intelligence. Hawkins is an American businessman, neuroscientist and engineer. He co-founded Palm Computing, where he co-created the Palm Pilot and Treo, and Handspring. He subsequently turned to work on neuroscience, founding the Redwood Center for Theoretical Neuroscience in 2002. In 2005 he founded Numenta Incorporated, where he leads a team in efforts to reverse engineer the neocortex, and enable machine intelligence technology based on brain theory. He is the co-author of On Intelligence, 2004, which explains his memory prediction framework theory of the brain, and he is the author of A Thousand Brains, A New Theory of Intelligence, 2021, based on his research in neuroscience. As a result of his studies, Hawkins proposes the hierarchical temporal memory, HTM neuron, that is a biologically constrained machine intelligence technology, and the sparse artificial intelligence model. Jeff Hawkins is an advanced researcher in the application of neuroscience to the development of artificial intelligence. As a result of his studies at Numenta Incorporated, Hawkins proposes the sparse artificial intelligence model, whose main characteristics are. As a result of his studies at Numenta Incorporated, Hawkins proposes the sparse artificial intelligence model, whose main characteristics are. The neocortex contains millions of neurons that communicate with each other, to capture the world that occurs around the human being. The connectivity of these neurons does not occur based on a dense network, that connects all neurons to each other. Connectivity is based on a sparse network, which can be assimilated to a sparse array. Neuroscientific studies associate the network of neurons of the cerebral cortex in layers, and in columns, connected in an organized hierarchical way. Hawkins proposes the sparse artificial intelligence model, composed of columns and layers that performs robust object learning and recognition. Columns integrate their changing inputs over time to learn complete models of observed objects. Lateral connections across columns allow the network to more rapidly infer objects, based on the partial knowledge of adjacent columns. Because columns integrate input over time and space, the network learns models of complex objects, that extend well beyond the receptive field of individual cells. The Hawkins network model introduces a new feature in cortical columns, that proposes that a representation of location calculated within the subgranular layers of each column. The representation of location is relative to the object being sensed. Pairing sensory features with locations is a requirement for modeling objects and therefore must occur somewhere in the neocortex. Hawkins proposes it occurs in every column in every region. The network model contains 2 layers and 1 or more columns. Simulations show that small single-column networks can learn to recognize hundreds of complex multidimensional objects. Given the ubiquity of columnar and laminar connectivity patterns, the columns and regions have more powerful recognition and modeling capabilities than previously assumed. This section is based on the paper, Why Does the Neocortex Have Layers and Columns? A Theory of Learning the 3D Structure of the World. Neocortical regions are composed of columns and layers that performs robust object learning and recognition. Columns integrate their changing inputs over time to learn complete models of observed objects. Lateral connections across columns allow the network to more rapidly infer objects, based on the partial knowledge of adjacent columns. Because columns integrate input over time and space, the network learns models of complex objects, that extend well beyond the receptive field of individual cells. The image shows the different parts of the human cortex. In summary, the modeling of the structure of neocortical regions is organized into columns and layers. Connections between layers run mostly perpendicular to the surface, suggesting a columnar functional organization. Some layers have long-range lateral connections, suggesting interactions between columns. Similar patterns of connectivity exist in all regions, but their exact role remain a mystery. All regions have a motor output. Hawkins' work gives rise to the HTM neuron, that is intended to emulate the overall structural and functionality of the human neocortex. The main properties of HTM is hierarchical structure, sparsity and modularity. The image presents the comparison between a normal, pyramidal, artificial neuron and a HTM neuron proposed by Hawkins. Hawkins proposes the concept of regions, groups of cells organized hierarchically, interconnected, but with a low density of links, sparse. This is the fundamental representation of the 3D connectivity of neurons in the neocortex. This structure has the same characteristics as those generated when a monolithic model is divided and decomposed into an atomized model, to process it in parallel. In mathematical models, it is common to use a matrix that relates columns with variables, and equations with rows. Hawkins' theories, which have been carefully studied by High, mainly the structure of the neocortex, are the basis for the union of the components of an artificial brain. Structurally similar to that of the human cortex. The image presents the hierarchical distribution of neurons in the neocortex, joining brain, neocortical columns, simple neurons and ion channels. This is the starting point of the Hawkins model. Hawkins proposes the concept of regions, groups of cells organized hierarchically, interconnected, but with a low density of links, sparse. In mathematical models, it is common to use a matrix that relates columns with variables, and equations with rows. The normal thing is that these matrices are sparse. Hawkins proposes the concept of regions, groups of cells organized hierarchically, interconnected, but with a low density of links, sparse. This is the fundamental representation of the 3D connectivity of neurons in the neocortex. This structure has the same characteristics as those generated when a monolithic model is divided and decomposed into an atomized model, to process it in parallel. The cerebral cortex stores all the connectivity of the neural networks that make up the brain. This diagram shows a 3-level structure. Result of partitioning and decomposition of a system, using a simple methodology of large-scale optimization, like Bender's theory or Lagrangian relaxation. Based on the concepts of partitioning and decomposition, it is possible to decouple a system, to obtain vertical structures partially similar like of the human neocortex. Cross-decomposition, developed by Van Roy, makes it possible to establish complex optimization processes, in which multiple methodologies are used on a large scale. This allows the problems to be adjusted to the most convenient methodology for the solution of each subproblem. This implies a universal conversation between multiple algorithms, built with different methodologies. Cross-decomposition makes it possible to establish complex optimization processes, in which multiple large-scale methodologies are used, which allows to adjust the problems to the most convenient methodology for the solution of each subproblem. It also frees the decomposed problem from bidimensional hierarchical tree-like structures, enabling horizontal communications between subproblems. From the point of view of multi-layer structures, cross-decomposition results in the exchange of information between multiple layers, of different columns, like the actual structure of the human neocortex. As in the human cortex, lateral connections between columns allow the network to solve problems more quickly, based on partial knowledge of adjacent columns. From the point of view of multi-layer structures, cross-decomposition gives rise to the exchange of information between multiple layers, of different columns, such as the real structure of the human neocortex. Cross-decomposition can be said to be a smarter scheme, due to the creation of new and more efficient connections in the artificial brain. The hypothalamus must coordinate all the processes that the human being carries out. The artificial hypothalamus must connect the multiple mathematical models, algorithms, that are part of the artificial brain, exchanging information between them to obtain a common goal, mathematically an objective function. This activity must be autonomous, permanent, and based on distributed processing. The artificial hypothalamus emulates the human hypothalamus as a computer-distributed processor that solves multiple problems, representing the holistic model of an organization. This process can be called autonomous real-time distributed optimization. The optimization methodologies to be used are selected by the artificial hypothalamus. Artificial hippocampus, storing the experience. Hippocampus store the experience, and the knowledge acquired over time in the human brain. The hippocampus. Storage structures and processes from the decision-making that must be faced permanently. The artificial hippocampus is based on the mathematical synthesis of the information generated by algorithms and problem-solving processes, to use it in new runs of these algorithms to speed up the problem solution in real time. Artificial hippocampus store, like in the humans, the experience, and the knowledge acquired over time. Mathematical modeling expert systems. A knowledge-based system, KBS, must store two types of knowledge. Mathematical components, equations, problems, models, previously used and working properly. This information is generated by the modeler who builds the mathematical models and their entire operating environment, and results of previous runs to speed up the solution of new problems. This information is generated by the math models when they are used, and correspond to the trajectories of the variables involved in these models. The use of this information is totally dynamic, since it depends on the value of the input parameters in each new run. In a very simplistic way, it could be said that the hippocampus stores information with two objectives to support human decision-making. Historical information of the models formulated and that work correctly. Historical information of the runs made with a certain model, in such a way to be able to use this information in new runs. The information is stored in the hippocampus where the data is organized according to its age. Like any physical element, its use affects its reliability, and that is why short memory, the one that stores the data of the last days, begins to fail with age, until it is lost, while long-term memory can store very sharp data, but that require greater access time to locate them. Remember the structure and functioning of an artificial hippocampus for advanced mathematical modeling, considering the basic structure of the human hippocampus, and its incorporation as part of an artificial brain that has an artificial cortex and an artificial hypothalamus. The operation of the artificial hippocampus is presented as an expert system that must store two types of knowledge: formulation, the components of mathematical models, and historical data of the results generated solving the mathematical problems. Using large-scale optimization methodologies, this information is used as starting point in future uses of mathematical models to support decision-making. The hippocampus. Storage structures and processes from the decision-making that must be faced permanently. The artificial hippocampus is based on the mathematical synthesis of the information generated by algorithms and problem-solving processes, to use it in new runs of these algorithms to speed up the problem solution in real time. In the artificial brain, knowledge corresponds to matrix structures, generated during the process of solving the different problems of the mathematical model, which are stored in disks clusters. The elements of these matrices are based on mathematical laws and have no subjective elements. The interested reader can consult the white paper. Artificial hippocampus: the energy of the artificial brain. How do human brains learn? 86 billion interconnected neurons make up the human brain, the product of billions of years of evolution. However, the mechanisms that underpin the evolution of this remarkable structure are still in the exploration stage. Donald Hebb is best known for his theory of Hebbian learning, which he introduced in his classic work The Organization of Behavior in 1949. Hebb has been described as the father of neuropsychology and neural networks. The central concept of Hebb's theory is summed up in the phrase, "cells that fire together, wire together." According to this idea, when an A neuron is repeatedly involved in the activation of a B neuron, the synapses between them are strengthened. Hebb's theory has shown that learning does not increase the number of neurons, but it does increase the connectivity between them. Donald Hebb, July 22, 1904, August 20, 1985, was a Canadian psychologist who was influential in neuropsychology, where he sought to understand how the function of neurons contributed to psychological processes such as learning. He is best known for his theory of Hebbian learning, which he introduced in his classic work The Organization of Behavior, 1949. Hebb has been described as the father of neuropsychology and neural networks. His views on learning described behavior and thought in terms of brain function, explaining cognitive processes in terms of connections between neuron assemblies. Hebb concludes that the persistence, or repetition of a repetitive activity, or signal, tends to induce long-lasting cellular changes, which promote its stability. When an axon of a neuron A is close enough to excite a neuron B and repeatedly participates in its activation, processes of growth, or metabolic change, occur in one or both neurons, so that the efficiency of A to excite B increases. According to Hebb's theory, humans learn if we form new synaptic connections between neurons. Learning is a new relationship that is created between neurons, and remembering is to keep that relationship socially active. When we're learning something new, neurons in different brain regions communicate with each other. With more exposure and practice over time, the brain creates stronger and more efficient communication between neurons. The central concept of Hebb's theory is summed up in the phrase, cells that fire together, wire together. According to this idea, when an A neuron is repeatedly involved in the activation of a B neuron, the synapses between them are strengthened. This principle suggests that the concurrence of neural activity is the basis for learning and memory. Synaptic strengthening: when a presynaptic neuron and a postsynaptic neuron are activated simultaneously, the connections between them are strengthened. Activity-dependent plasticity: the efficiency of synaptic connections is not static but can be modified as a function of neuronal activity. This plasticity is essential for adaptive learning and memory. The question to be answered is whether learning is due to the creation of new cells, neurons, in the brain. The answer is simple: no. Then, learning is not about new cells, but about new connections. Because of the creation of new and more efficient connections in the brain. The image shows the evolution of the density of a network, which is a measure of the learning that the subject has acquired throughout its evolution. Higher density means more learning. In the figure, each circle represents a neuron, and each arc a connection. Over time, the human hippocampus, or the artificial hippocampus, becomes filled with connections. Artificial neural nets. In 1943, Warren McCulloch and Walter Pitts created the concept of artificial neural networks. They published the paper, A Logical Calculus of the Ideas Immanent in Nervous Activity. McCulloch and Pitts tried to understand how the brain could produce highly complex patterns, by using many basic cells that are connected. They designed their system based on as they believed our brains work, and patterned it after the biological model of how neurons work with each other. The neural networks were growing, and in practice they took the name of artificial intelligence, displacing other methodologies and technologies that also generate artificial intelligence in the machines. Within a nervous system, a neuron is an electrically excitable cell that fires electrical signals called action potentials through a neural network. The neuron is the main component of nervous tissue in all animals. Neurons communicate with other cells through synapses, specialized connections that commonly use minute amounts of chemical neurotransmitters, to pass the electrical signal from the presynaptic neuron to the target cell, across the synaptic gap. Neurons are highly specialized for the processing and transmission of cellular signals. Given their diversity of functions performed in different parts of the nervous system, there is a wide variety in their shape, size, and electrochemical properties. For instance, the soma of a neuron can vary from 4 to 100 micrometers in diameter. An artificial neuron is a mathematical function conceived as a model of biological neurons. Artificial neurons are elementary units in an artificial neural network. The artificial neuron receives one or more inputs, representing excitatory postsynaptic potentials and inhibitory postsynaptic potentials at neural dendrites, and sums them to produce an output, or activation, representing a neuron's action potential which is transmitted along its axon. Usually each input is separately weighted, and the sum is passed through a nonlinear function known as an activation function, or transfer function. The transfer functions usually have a sigmoid shape, but they may also take the form of other nonlinear functions, piecewise linear functions, or step functions. They are also often monotonically increasing, continuous, differentiable, and bounded. Transfer functions usually have a sigmoid shape, but they can also take the form of other nonlinear functions, piecewise linear functions, or step functions. They also tend to be monotonically increasing, continuous, differentiable, and bounded. An artificial neural net is based on a collection of connected artificial neurons, which loosely model the neurons of a biological brain. Each connection, like the synapses in a biological brain, can transmit a signal to other neurons. An artificial neuron receives signals, then processes them, and can send to neurons connected to it. The signal at a connection is a real number, and the output of each neuron is computed by some nonlinear function of the sum of its inputs. The connections are called edges. Neurons and edges typically have a weight that adjusts as learning proceeds. The weight increases or decreases the strength of the signal at a connection. Neurons may have a threshold such that a signal is sent only if the aggregate signal crosses the threshold. Defining parameters and topology is a combination of empirical work and scientific work, but there is no mathematical theory that must be respected. The algorithmic process is cyclical, and its convergence is based on the minimization of errors. The precision and representativeness of the process are directly proportional to the number of neurons that can be handled, which is why the development of associated technologies is exponentially enhanced, with the enhancement of computer technologies. Starting from the perceptron, the first artificial neuron created, the knowledge of neuronal modeling has evolved, currently having multiple types of artificial neural nets, specialized in performing specific pattern recognition. For this, the basic patterns of ANNs are modified. To handle the concept of mathematical intelligence, High developed the concepts of mathematical artificial neural nets, MANN, which complement the concepts of artificial neural networks, ANN. High developed a theory for building networks of artificial neurons specially built to integrate the artificial brain and fit into the structures of the artificial cortex. Starting from the perceptron, the first artificial neuron created, the knowledge of neuronal modeling has evolved, currently having multiple types of artificial neural nets. This new type of neuron will be called mathematical artificial neuron. Its name was derived from the fact that the neuron is built, based on mathematical models that represent a system, and that it contains logical or intuitive elements. The mathematical artificial neuron is a mathematical model, presumably of optimization, which results from the partitioning and decomposition of a monolithic problem into an atomized model, following the mathematical laws of large-scale mathematical modeling. Two mathematical artificial neurons communicate with each other, forming a network of mathematical artificial neurons. Communication occurs in two directions between the two neurons. The communication protocol between the two neurons is defined by mathematical laws developed to solve atomized problems. The modeler can choose the protocol, but not the communication process, which for optimization is based on the scientific laws of duality theory, and for equilibrium problems in mathematical programming with equilibrium constraints, PEC, methodologies. A mathematical neuron represents a robot, which can communicate with another robot, autonomously, since it knows the mathematical rules that it must respect. This is what happens in the human brain, where autonomic systems communicate with each other to make decisions. The mathematical artificial neuron is the technological evolution from the biological neuron, typical of mental intelligence, to the neurons necessary to represent mathematical intelligence, which until now are not produced by the human being. Like all mathematics, theory is cadent, and for those of us who already work in high-complexity mathematical modeling, it is the logical step we must take. It's just widening the look, and thinking a little outside the box. The mathematical artificial neuron is a mathematical superstructure, representing a complete system. A mathematical artificial neuron network can be a neuron of a larger mathematical artificial neuron network. This law of transitivity is typical of large-scale modeling. A large-scale system can be represented by a mathematical artificial neuron, and covers multiple subsystems, where each of them can be represented by a mathematical artificial neuron. This process can be repeated, until the smallest mathematical artificial neurons, the atoms of the system, are obtained. Using large-scale methodologies, the mathematical artificial neuron can be divided into two, or more, mathematical artificial neurons, forming a mathematical network of artificial neurons. This process can be repeated, until the smallest mathematical artificial neurons, the atoms of the system, are obtained. When the atomization of the system is pushed to the limit, the atom of the system will be the operation of the system over a period of the planning horizon, under a specific random scenario. How Hopfield neural networks learn? High enthusiastically celebrates that John Hopfield and Geoffrey Hinton have won the 2024 Nobel Prize in Physics for foundational discoveries and inventions that enable machine learning with artificial neural networks. This recognition is a stimulus, and a voice of encouragement, for all artificial intelligence scientists. John Joseph Hopfield, born July 15, 1933, is an American physicist and emeritus professor at Princeton University, most widely known for his study of associative neural networks in 1982. He is known for the development of the Hopfield network. Before its invention, research in artificial intelligence, AI, was in a decay period or AI winter. Hopfield work revitalized large-scale interest in this field. In 2024, Hopfield, along with Geoffrey Hinton, was awarded the Nobel Prize in Physics for their foundational contributions to machine learning, particularly through their work on artificial neural networks. He has been awarded various major physics awards for his work in multidisciplinary fields including condensed matter physics, statistical physics and biophysics. Hopfield's seminal paper is Neural Networks and Physical Systems with Emerging Collective Computational Capabilities. Published in 1982. Given the dynamical electrochemical properties of neurons and their interconnections, synapses, we readily understand schemes that use a few neurons to obtain elementary useful biological behavior. Our understanding of such simple circuits in electronics allows us to plan larger and more complex circuits which are essential to large computers. Because evolution has no such plan, it becomes relevant to ask whether the ability of large collections of neurons to perform computational tasks may in part be a spontaneous collective consequence of having a large number of interacting simple neurons in physical systems made from a large number. Hopfield networks are a form of recurrent neural networks that hold a prominent place in the history of artificial intelligence and artificial neural networks. They represented a significant advance in understanding how neural networks composed of simple, interconnected neurons could process information collectively. This model was inspired by both biology and physics. One of them is the Hopfield networks. The Hopfield network consists of binary threshold neurons, meaning they have two states, on or off, with each neuron interconnected, forming a fully interconnected network. This Hopfield ANN is characterized by associative ANN, unsupervised offline learning of the Hebbian type, monolayer, which means that neurons are input and output, and have no hidden layers, and to communicate with each other, neurons have lateral connections, but they do not have connections with themselves, they are not recursive. During the learning process, the ANN does not require cycles, iterations, but it does require an operation. The diagram presents the processing of Hopfield's neural network. An example of an ANN Hopfield application is pattern recognition. The paper, and the paper video. Hopfield networks is all you need. Present a good introduction to Hopfield networks. Another video that explains how the Hopfield RNA works. How are memories stored in neural networks? The Hopfield network. It is important to note that in Hopfield's model, based on Hebb's functioning, there is no hippocampus that stores what has been learned. This knowledge is concentrated in the weights of the neural network. A video that explains how the Hopfield RNA works is a brain-inspired algorithm for memory. Human learning, machine learning, and algorithm learning are the actual modes of learning. Today, the term human learning refers to the biological and psychological process by which human beings naturally acquire knowledge and direct learning via the neuroplasticity of the brain using technologies originating in Industry 4.0. Machine learning is a branch of artificial intelligence that allows computers to learn and improve their performance autonomously from data, without being programmed with explicit instructions for each task, uses algorithms to identify patterns, detect mathematical relationships, and generate accurate predictions about new information. Algorithm learning is the learning carried out by an algorithm, which participates in a machine learning process, so that the next time it can use information from the past, and if possible, improve performance. The stages of teaching and learning have occurred throughout the entire life of humanity, and they have been its means of development. Starting with human learning, in which humans teach humans, and humanity evolves slowly, this stage begins to change in the middle of the last century. Since the invention of computers, scientists begin the process of giving them the ability to solve real-life problems. This could be called the birth of machine learning, in which humans teach machines by making the algorithms that are the basis of artificial intelligence. This is the era we live in, which has the peculiarity that these algorithms are mass-produced and commercially sold to machine learning users. The next logical step is called by high algorithm learning. At this stage, machines will learn to create algorithms without human involvement, and algorithms will learn autonomously to improve their behavior. This is a necessary step to arrive at the artificial general intelligence, AGI, the dream of scientists. Neuroplasticity is the brain's ability to change its structure and functioning in response to new experiences, learning, and stimuli from the environment. Basically, learning is physically rewiring our brain. When you learn something new, neurons communicate with each other using electrical and chemical signals, or brain algorithms. If this activity is repeated frequently, the connections, synapses, are strengthened; if they are not used, weakened, or removed, synaptic pruning. This plasticity allows networking. Learning creates new neural pathways. For example, when learning a language, your brain maps new sounds and meanings. Constant adaptation, it is not something exclusive to childhood. Although it is maximum in the early years, the brain can change and learn throughout life. Compensation, if one area of the brain is damaged, as in a stroke, plasticity allows other areas to reorganize to take over lost functions. Direct learning driven by technology. Ray Kurzweil is a 78-year-old American inventor, writer, and futurist, widely known for his predictions on artificial intelligence and biotechnology. Currently, he serves as Director of Engineering at Google, where he leads natural language processing projects. Kurzweil predicts that humans will develop emotions and characteristics of greater complexity due to the connection of their brains with computers, and that by 2045, non-biological intelligence will be 1 billion times more potent than all current human intelligence, marking an irreversible singularity in civilization. On a commercial level, these services have been available for several years, for example, skull tomography, used to detect bleeding, tumors, fractures or brain injuries after an accident. Magnetic resonance imaging, ideal for accurate diagnosis of frequent headaches, providing pain-free high-resolution images. Brain ultrasound, generally focused on soft tissues and specific cases. What is new will be the public use of these technologies for the learning process of the human brain. Direct learning powered by nanotechnology. In the 2030s, human brains will connect to the cloud, allowing us to send emails and photos directly to the brain, and back up our thoughts and memories. This will be possible thanks to nanobots, small robots with DNA strands that swim in the capillaries of our brains. It will be just as the use of learning tools has been for human beings. The concept of learning through nanobots is at the intersection of advanced nanotechnology and neuroscience, posing a future in which knowledge will be transferred directly to the brain, or where our cognitive abilities will be artificially enhanced. There is currently research that lays the groundwork for this type of interface. Some examples are thought control. Prototypes of DNA nanobots controlled by human brain activity have been developed. In proofs of concept, a human operator has activated nanobots inside a living organism simply through cognitive effort. Neural nanorobots. MIT researchers are working on devices such as the Cell Rover, nanometer-scale antennas that can enter cells and transmit signals without damaging them, allowing precise electrical stimulation of individual neurons. Biological sensors. Nano devices capable of monitoring biomarkers in real time, which will evolve into systems that detect cognitive fatigue or optimal learning states to intervene biologically. High algorithms learning. Algorithms that learn during the solution process. How high algorithms learn? Unsupervised learning. As part of the research process on artificial business brains, which aims to provide businesses with the ability to lean on artificial management across the organization, HI has developed the ability to manage the generation of knowledge that produces large-scale optimization algorithms. In essence, this type of learning is unsupervised, but in its use, it can be improved by giving it the ability to supervise, creating a new level of learning for the selection of knowledge to be used in each new execution, based on Hopfield's neural networks. The image shows the evolution of the density of a network, which is a measure of the learning that the subject has acquired throughout its evolution. Higher density means more learning. This means that a process of learning of an algorithm involves increasing the density of the problem-solving space, as information about the solution of the problem is obtained with each execution that is performed. This is the way large-scale methodologies work. From the point of view of a hippocampus, which operates all the time, the space for solving problems fills up as new experiences of new runs emerge. Mathematically, this implies that the number of constraints that represent learning is increasing. Therefore, the learning process of an artificial brain involves increasing the number of connections that are mapped into the artificial cortex. This means larger and/or denser matrices. While mathematical models on digital computers, and the data storage disks, date back many years, more than 60 years, and despite the Industrial Revolution 4.0, how to run a model, it does not seem to have evolved. The normal process is: the model is thinking monolithically. A high-performance solver is selected to solve the problem. The results are post-processed, and the results of the models are stored, with administrative purposes. Usually, in the next run, the model starts from scratch, ignoring the past, that is, it has no memory. In some cases, it is heated from a starting point provided by the last run, presumably the last optimal solution, or a point that ensures feasibility. However, an artificial hippocampus, designed for the artificial brain, can take advantage of a lot of information produced within a run, and during the history of all runs. Two examples will be briefly presented: handling of Bender's theory, and generation of convex Hull. In 1962, the Dutch mathematician Jacques Benders publishes his theory of partition that is a transcendental step, not the first, in parallel computing, aimed at solving complex mathematical problems, dividing them into more elementary subproblems. Artificial brains are based on multi-problem mathematical models, the solution of which must be addressed with large-scale optimization methodologies. As an example, we will analyze the construction of an artificial hippocampus using Bender's partition theory. Benders divides the model of a system into two: a coordination problem and a dependent problem. To solve the model, a conversation is established in the two problems. The solution of the model involves a conversation between the two math problems, or agents. The coordinator, over Y, variables controlled by the board of directors, and the subproblem, over X, variables that are controlled by the production manager, and that depend on the decisions of the board of directors. In its original form, Bender's algorithm involves a sequential conversation between the coordination problem and the slave problem. In non-mathematical terms, the board of directors sends a set of technical decisions to the production manager to assess their impact, that is, the marginal costs and benefits, for all resources, which are the economic indicators of the board's decisions. With this information, the board analyzes the optimality of its decisions and, if not, sends a new proposal. The process involves the partition of the monolithic model into two smaller problems, the coordinator and the subproblem. This will reduce memory and processing time requirements. This division does not produce knowledge to solve the model, it simply produces two problems, which only together can solve the model. To solve the problem, Benders devised an algorithm in which the coordinator captures the information provided by the subproblem, through constraints, called cutting planes, in red, in such a way that, under certain mathematical conditions, the algorithm converges to the optimal solution. At the time of convergence, the cutting planes represent everything that the coordinator learned from the subproblem, and the subproblem is not necessary. If only certain parameters change, the next time the issue runs, the subproblem may not be necessary. Like any optimization problem, this one has a matrix formulation that High has associated with the artificial cortex. The problem is divided into the coordinator, psi-bt, and the slave, SPBT, each with its own connection network in the artificial cortex. Splitting the problem is splitting its matrices. When starting the optimization process, there are no cutting planes and therefore this part of the problem does not exist in the artificial cortex. Psi-bt includes two types of cuts that limit the feasibility zone of Y, in other words, indicate decisions that cannot be made by the CEO. The first type, that we call optimality cutting planes because the cut eliminates values of board decisions that can't be optimal every time the slave problem is solved, until the optimum, or until a nearby feasible solution, a cut of this type is generated. The second type, the feasibility cutting planes, restricts the feasible zone of board decisions to maintain feasible solutions in the production problem. Every time the slave problem produces an unfeasible solution, a cut of this type is generated. The second type, the feasibility cutting planes, restricts the feasible zone of board decisions to maintain feasible solutions in the production problem. Every time the slave problem produces an unfeasible solution, a cut of this type is generated. The coordinator's solution implies a learning process in the algorithm, which is configured with the minimal connectivity. As iterations occur, the number of connections in the artificial cortex increases, which corresponds to the learning of the algorithm, that is part of the artificial brain. If the dual variables of the subproblem of each iteration have been stored in the artificial hippocampus, when the process stops, and starts again, including the previous cutting planes, everything will be faster in the second run, implying that the brain has learned from one run to the next. Artificial hippocampus. Storing the history of runs. Following the principles developed by Benders, it is possible to build an artificial hippocampus that remain active and useful beyond the duration of a run of a computer model. To do this, the cuts generated in each run must be stored in such a way as that they may be used later. This implies a coordination work, since it cannot be guaranteed that the information as it is produced can be reprocessed later. An artificial hippocampus stores cuts from one run to be used in the next, which will produce new cuts. High is researching in the creation of methodologies to generate new rules that fit the dynamic variation of the parameters that affect the models. While all the mathematical support is solid, there is no theory that can indicate which cutting planes should be selected when restarting the model. Problem that becomes big when the size of the database grows. For this reason, it is considered necessary to develop tools based on traditional artificial intelligence, artificial neural nets, to help the management of the hippocampus database. The idea is that for very large problems, the selection process will include an ANN. This is one of High's research projects. High is working on the use of convolutional neural networks to select the cutting planes to be extracted from the memory of the artificial hippocampus, to incorporate them into the mathematical problem whose solution algorithm is in a continuous learning process. High is testing the use of Hopfield neural networks to select the information stored in the database. Another alternative to generate knowledge that is stored in the artificial hippocampus is the generation of convex hulls, associated with optimal solutions of the mathematical problems. The multidimensional grid that represent the convex hull can be incorporated into the integrated problems to accelerate the solution process. Depending on the specific problem, the convex hulls may be permanent, or they must be recalculated dynamically when the parameters of the mathematical models change. The convex hull is associated with parts of problems that are solved independently and then incorporated into multiple runs of the parent problem. The example shows the convex hull representing the pumping stations that are part of a pipeline operation problem. Convex hulls allow flexible approaches, as in the case of an energy transmission system, in which they can be associated to two different ways to solve the problem flow AC and DC flow. The production of convex hull of optimal points is a standalone process, therefore they can be generated outside the optimization process. As iterations occur, the number of connections in the artificial cortex increases, which corresponds to the learning of the algorithm, that is part of the artificial brain. If the dual variables of the subproblem of each iteration have been stored in the artificial hippocampus, when the process stops and starts again, including the previous cutting planes, everything will be faster in the second run, implying that the brain has learned from one run to the next. Artificial hippocampus. Storing mathematical components. Optex, High's artificial intelligence to develop artificial brains, manages the artificial hippocampus. It is oriented to make high-complexity large-scale mathematical models without programming. The models are built in a modular way, as if they were a Lego set, which are formed by a compatible system of equations, the Leo parts, for all models. When considering that an artificial brain will gather, in an integrated way, the mathematical models required by an organization, we must be aware that a traditional approach, based on programmers, is a very difficult path, if not impossible. As everything has evolved, HI has developed OpTeX, the artificial intelligence to produce artificial intelligence algorithms. The interested party is invited to watch the video. Making high-complexity large-scale mathematical models without programming. Industry 6.0. The artificial intelligence genius is out of the bottle. Industry 6.0 marks the beginning of the ecosystem era, where industrial systems go beyond simple automation to function as fully autonomous and self-repairing living organisms. The catalyst is the convergence of neuroscience and artificial intelligence. This biological symbiosis displaces the factories of rigid pre-programmed rules towards a state of distributed, adaptive and biological superintelligence. The fundamental pillars of Industry 6.0, unlike Industry 4.0, digitalization, and Industry 5.0, human-centered collaboration, are an integration of human-machine biology. The convergence of neuroscience and Industry 6.0 manifests itself in several key domains. Neurocognitive interfaces, advanced brain-machine interfaces transition workers from mechanical control to thought-based orchestration of cognitive robot swarms. Neuro-inspired AI, artificial intelligence architectures discard rigid coding, evolving like biological neural systems to handle massive, asynchronous industrial variables. Human-machine biology symbiosis, human intuition fuses with adaptive synthetic materials and neural frameworks, blurring the line between the living and the artificial. Socio-cognitive smart ambience, industrial workspaces adapt in real time to the emotional, cognitive, and fatigue status of the human workforce. An artificial intelligence without dynamic memory and automatic learning capacity, it can't be smart. RCADT is the most applied academic center in the integration of the teaching of mathematical programming and artificial intelligence. For more information you can consult the URL. Remember, all science as it grows toward perfection becomes mathematical in its ideas. Alfred Whitehead. Thank you very much for your attention.